and I teach physics and astronomy here at Andover, and I'm the supervisor of the Phillips Academy Observatory. So um, I run this place, and I'm actually coming to you from the observatory tonight. You can see the telescope in the background, and the plan for this evening is to I'm going to show you how the telescope operates, and we're going to use our fancy astronomy camera to take some pictures of things to just give you a sense of how things go. So it's a kind of virtual star party that we're having here tonight. And I have a couple of students along with me this evening. So I'm going to have them introduce themselves. And I asked them to prepare some notes about the different objects. And so they'll jump in and talk about things. But this is really meant to be a fun and casual evening. So if you all have questions or things you want to offer, responses to the things we're seeing, feel free to just jump in at any point. But let's start with some introductions from Lexi and Claire. Go ahead, you guys.
All right, so hi, I'm Claire. I'm currently in Andover. I'm a day student. I live about 2 miles from campus, so that's pretty fun. I guess on campus besides astronomy, well, I'm the co-president of the astronomy club, so not necessarily besides astronomy. I'm also a dancer along with Lexi, and I'm a rising senior.
Hi, I'm Lexi. I'm also a rising senior, and I'm from Bermuda. Apart from astronomy on campus, I am the captain of varsity dance, and I'm also the captain of the jazz dance club on campus, Blue Stripe.
All right, thanks, you guys. So I'm gonna, I guess, first of all, I'll just point out this is our telescope, and you can kind of see the observatory. It's quite large in here. And actually, on a typical reunion weekend, we would have a chance for alumni to come up to the observatory and actually look through the telescope to observe things. But since we can't do this evening, we're going to do it a different way. Oh, and we have one more student that has just arrived. Troy, would you please introduce yourself?
Yeah, hi, I'm Troy, and I'm calling in from China. Sorry that I'm late. I had some internet issue just now.
No problem, Troy. Thank you for joining. Do you want to say anything else about yourself?
Yeah, sure. I'm a rising senior, and on campus, I also do ceramics.
All right, great. So I'm going to share my screen, and what I want to start with is I wanted to show you the software that we use to control the telescope. So we've been remote for parts of the year, teaching remotely and learning remotely. Sometimes the kids have been on campus and sometimes they've been off campus. And one of the great things about this observatory is that it's automated. So the telescope is run by the computer, and I can actually call into this computer right from home. So from my living room, I can just basically call up the observatory computer and operate it. And I can also, of course, interact with students over Zoom. And there's a feature in Zoom that allows you to take control of another person's desktop. And so what we would do during the school year is I would call into the computer, and then I would call with the students by Zoom. They could actually operate the telescope themselves. So this is a picture of the sky, and I'm going to zoom out a little bit so you can see it more easily. So this software is showing us all of the things that are above the horizon right now from our location. So it knows where we are and what time it is, and so it can make this map of the sky. It's showing the telescope is right here, and it's really easy to move the telescope around. You just click another point in the sky and then click go to, and I'll kind of move my camera so that you can watch the telescope. So you want to kind of watch my picture, and you can see the telescope move. Did you see that? I'll move it quite a bit to another part of the sky so that you can see it pretty easily. And so you can see it just kind of swings around and goes to wherever we want it to go. Now, the dome has a slit that you can see here, and so the dome needs to move around so that the slit is aligned with the telescope, and I'll do that in a minute when we first pick our first object. But what we're going to do now is go to our first object, and we're going to take a picture of it, and I'll show you how the camera software works in a minute. So I think I'll start with something that I know is a relatively bright object. It's just starting to get dark in Andover. It's not even completely dark yet. And M13 is a nice, relatively bright object that I think we'll be able to get even before it's completely dark. So the telescope's going over there, and I'm gonna move the dome, and I'm actually just doing this by hand. This can be done automatically, but I'm doing it by hand tonight. So I'm gonna try to orient. It's a little bit hard to show this, but I'm gonna do it. I guess maybe you'll see in a minute the slit come into view. So we just replaced the telescope about a year ago, and you can appreciate that the dome moves much less quickly than the telescope does. That telescope has a really nice design. Anyway, the telescope is now aligned with the dome. And the next thing we're gonna do is just to snap a picture here. I'm gonna do one thing first though. No, I'm not. Yes, I am. I got one thing I want to take care of. If I can. I'm not going to do that at the moment. Oh, this is a picture from last night. Okay, so we have, in addition to the telescope, you can see a camera on the back end of the telescope right here. So this is a camera, it's a digital camera with a CCD chip inside. And it is a really sensitive camera that detects just about every photon that hits the chip is detected by this camera. And it also has a software that we use to run it. It's called MaximDL. And it's really easy to use. This is the control window. And I'm just going to take a quick exposure, like a 5-second exposure, and see what we get. Now, I do have a bright light on in the dome, so I'm going to turn that off. I wanted you to be able to see my face when this whole thing started. And actually, I guess my face is still illuminated by the computer screen. But there you go. So it's kind of, to tell you the truth, I'm looking at this and thinking it's not a very good picture. There's a lot of bright area in the center. That's because I had that bright light on. So let me just take another picture and you can see how it improves. The other thing I'm not too happy about is that it's not very well centered. And I'd like to improve that. And I think I'll have a chance to do it. But let's just see what happens. Did that not get any better? Is that the same, essentially the same thing? You can see down here the exposure being taken, it's just a 5-second exposure. And it's, you know what, it is getting better because it's getting slightly darker.
All we can see is you, babe, not the guy.
What's that? Okay, so what I'm gonna do is I'm actually gonna put it on continuous mode, and I'm just gonna start, and what it does here is it takes an exposure, a 5-second exposure, and downloads it, and then it just takes another one right away. And what we'll do is we'll leave it there for a minute, and you can sort of appreciate how it's getting darker. Now, while we watch these images come in, Troy could you tell us a little bit about M13? Do you have that one prepared? If not, I can say something about it, maybe.
I don't think I saw your email on that one.
All right, that's okay. So do you have anything about a globular cluster? Do you want to say anything about globular clusters, or does anyone? Meanwhile, I'm looking for this. Oh, this is what I want. I want to nudge the telescope. See how it's slightly off center? I'm going to nudge this thing a little bit to the north, and that's going to center it up. All right, well, I'll say something about globular clusters. Oh, Lexi, do you want to say something about globular clusters?
Yeah, globular clusters is kind of really what it sounds like. It's just like a spherical like area, I guess, or just like spherical clump of just like a ton of stars. So it's like really tightly bound by like, since they're like such high like masses, all the stars they're really tightly bound by like gravity, which is why they're like all just like in this big spherical clump. Yeah.
Excellent. In general, when you see a star cluster like this, the stars have all formed in the same region. And in some cases, the stars that form in a region kind of hang together like this in a globular cluster, and they will be together forever. They're gravitationally bound. And in other cases, the stars are kind of together, but sort of randomly associated with each other. And those are called open clusters, and those tend to kind of drift apart over time. So our own sun was formed in an open cluster, and the stars have drifted apart over time, and it's no longer in a cluster. But some astronomers are really interested in kind of trying to figure out what the other stars were in the association that the sun was born in. So this is M13, the Hercules cluster. And let me just, I'll stop this for a minute, and I'll go back to my sky program and just show you, this is Hercules. And Hercules kind of has a club, and that's the head and the body and an arm and some legs. And the Hercules cluster is right here up in the head of Hercules. All right, I'm going to pause here for a moment.
Hey, Caroline, I had a question for you. What
Good.
keeps those stars from collapsing into each other? Is there some sort of an
Yeah.
orbit or a rotation?
Great question. Yeah, so I'll try to answer the question by making a connection. The moon is orbiting the Earth, but it doesn't crash into the Earth because of the fact that it's in motion. So the Earth is pulling on the moon gravitationally, which makes it go in its elliptical orbit, but it doesn't ever actually pull the moon into the Earth so that it crashes into the Earth. And in the same way, the gravity of this system is allowing the stars to orbit their common center of mass, but they don't actually crash into each other. They just continue to orbit this common center of mass. Does that help? And is that Mr. Broderick, my teacher from high school?
It is, and it does.
Welcome. It just happens. I went to Nobles. I didn't go to Andover, but Mr. Broderick taught at Nobles, and it's just a very fun thing that we've seen each other over the years at some of these reunions. So do you guys want to see something else? How are we doing so far? Is this okay? This is kind of my plan. We move the telescope around, look at some stuff, and have a good time. This is how a virtual star party works. So I hope that this is going to work for people.
This
All right.
is great.
Okay, good. I'm glad you're happy. I want you to be happy on your reunion weekend. So I'm happy to hear that it's going okay so far. So M92. Let me just peek at my notes here. Yeah, that's another globular cluster. So I'm gonna go over here closer to the club of Hercules, and I'm gonna move my telescope, and then I have to flip around and check to see if the dome needs to move a little bit. It does, so I'm gonna do that. Excuse me for a moment. So I didn't have to go too far, And now I'm gonna switch back over to my camera software. It's a little bit tough with all of these windows, and I wanna be able to see at least some of you at the same time. What I really need is an external monitor so that I can see all of your faces on one screen and see the telescope stuff on the other screen. But anyway, okay, so we're at another globular cluster. So let's see what this one looks like. So I'm gonna start my images here, and we'll go for the 5-second continuous images again. It's kind of amazing that you can get such a complete image in 5 seconds. Okay, so what do we see here? This one looks a little bit more kind of clumped together. So, you know, yeah, that's true. It has a slightly smaller angular size from our perspective. I'm gonna go back and nudge it again. For some reason, it seems that the images are always just a little bit off. I think my telescope has settled since we first installed it. And so it's always just a little bit off. So I always just nudge it a little bit to the north, and then things are usually okay. So I think the next image will be pretty good. You can sort of see that it moved during that last image, and you can see the star trails. And I got a good feeling about this one. Okay, there it is. Anyone have anything to say about this one, students? We may have missed a memo about preparing notes about these things, but we will have some comments on some of these clusters in a bit, or some of these objects in a bit. Let me stop here for a moment and go for a slightly longer exposure. And the reason I want to do that is because this is, I mean, it's incredible. 5 seconds, we're already basically able to see this star cluster. But there are a lot of field stars out here that you're not able to see in a shorter exposure. And so a lot of times what astrophotographers will do, when you see like a really amazing image on the internet or something like that, what they're typically doing is taking some very short exposures to get details in the really bright part of the image. And then they'll take some longer exposures to get details in the image, you know, in the parts of the image that are not so bright. And then they have fancy ways in Photoshop and things like that to get it all together. So that's kind of cool. You see that improvement? Let me stop and go for something a little bit longer even. Let's go for a 30-second exposure and see what we get there. So these globular clusters are all within the Milky Way galaxy, the ones that we're looking at, though of course there are globular clusters in other galaxies as well. And the globular clusters were used at one time to figure out the approximate location of the center of the Milky Way galaxy. They're spread kind of in a uniform way in the outer parts of the galaxy. And so by looking at the locations of those globular clusters, they were able to basically find the center, the kind of center of mass of the globular clusters and figure out where the center of the Milky Way was by looking at those. So they're neat, and they're really old too. These things are very old objects. I think we already had our first 30-second exposure come in. So this one should look exactly the same. So I'll stop it after this one. All right, so there it is. So looking pretty good. The other thing you can do is in this camera software control system, you can kind of adjust the brightness, and sometimes you can bring out some of the finer details by adjusting the brightness. It doesn't look like there's too much to be done here, but that can be kind of a fun activity. So it's already getting dark in Andover. And so now we are gonna have access to some other interesting things. Oh, I didn't mean to open that one. So let's see where we're gonna go next. But does anyone have a comment while we wait?
Do you have an elliptical galaxy you can show us?
I have some spirals.
Spiral galaxy.
Let's go. But actually, I don't know who that is that just said that, but if you don't mind, oh, hi, Kelly. May I show you an open cluster first, just while it gets a little bit darker, and then I'll show you some awesome galaxies. Does that work for you?
Yeah.
All right, great. So M29. I have to remind myself about where that is. Let's see if I can find it on here. Otherwise, I might go with your plan. I thought M29. Let's see here. Ah, there it is. Okay, M29. So we're going to go over here. This is an open cluster, and I just feel like for completeness, after I have shown some globular clusters, that I should show an open one. So I'm going to move the dome. I'll be right back. All right, we're in good shape. This is pretty close to the horizon. And why does that matter? Well, let me get my image going and then I'll tell you. But first, I'm going to just, I know that I need to nudge my telescope each and every time. The dome is moving on its own right now. So I'm gonna get this started and tell you about why it matters that we're near the horizon. So when the telescope is pointed straight up, it's actually, the starlight is having to pass through less atmosphere than when the telescope is at a steeper angle closer to the horizon. It has to pass through, the light has to pass through more atmosphere when you're closer to the horizon. So as a result, astronomers will typically try to go for objects to observe that are closer to the zenith, closer to being straight overhead. And but this one seems to be working out pretty nicely. So I'm just going to change I had changed the screen stretch, so I'm going to go back. So this is M29. And remember I mentioned that for the open clusters, the stars are not so densely packed. And here you can see that. These open clusters tend to be young. And so there are usually some bright, hot, young stars in here. And you can see these bright stars in here. And again, these are not gravitationally bound. So over time, they'll just kind of drift away from each other, but they look very nice while they're all together. And so that's an example of an open cluster. All right, so you have inspired me. I think we should go straight to some galaxies. Although I don't have an elliptical galaxy on my list, but I can find one. But let's go to some of these. Let's go to some of these kind of showstopper galaxies to start. I'm looking for, let's go here, M101. This is a really good one.
Do you want me to give my notes on it?
Yes, I do. Absolutely, Lexi.
Okay. So
until it comes up though, should we? Let's hold on for a second.
okay.
I'm just checking to make sure that my dome is well aligned here. So what we're gonna do for this one, I think, is we will take a 30-second exposure just to warm everyone up so that you can get a sense of what we're gonna be seeing here. The dome kind of has a mind of its own. I'm just gonna wait for it to stop and then we'll take the image. I don't know why it's moving so much. Okay, it stopped. The telescope is very close to the zenith, so I was very happy with where the dome was, but I guess it had other ideas. All right, so I'm going to take a 30-second exposure of M101, and then when it comes up, Lexi, I'll actually go for something like a 90-second exposure, so you can give your notes on that one, and then we'll see an even better image after the slightly longer exposure. We'll get something up here for you so that you can talk about it.
Can you say why the numbers all begin with the letter M?
Oh, thank you for asking. Did you want to say, Lexi?
Messier,
Yeah.
Charles.
It's basically like the person who found it, Charles Messier, he like was an astronomer who found like a ton of like just like both nebulae and galaxies and just like celestial things like in his time. So in his catalog, all of his like things that he found start with M, which is why we have like M51, M101. It's just because of like Messier, which is his last name.
I see. Thank you.
Excellent. All right, so you can see a kind of hint of this spiral galaxy here that Lexi's going to talk about. And you can also appreciate how bright those first couple of objects must have been, because we were able to see them after just 5 seconds, right? And here, even after a 30-second exposure, things are looking, they're kind of hard to see. So I'm going to go for a 90-second exposure and get that going. And then Lexi, I'll turn it over to you. Go to it.
Okay, so M101, it's also known as just like the Pinwheel Galaxy. It's about 21 million light years away, and just like diameter wise, it's 6.4 megaparsecs, sorry, 6.4 megaparsecs, and has a magnitude of around like 7.8. It's found in the constellation of Ursa Major, which most of you should know, just like the Big Dipper, yay. It's about 70% like bigger than the Milky Way galaxy. And as for its like chemical makeup, I guess, it has tons of like hydrogen 2, which is like giving a lot of like hot spots like within like the actual arms of the galaxy that we'll see like after the 90-second exposure.
Awesome. I may run downstairs after this. I have some lights on in the observatory because I thought it would help you to see me, but now I realize that my computer screen is easily illuminating my face, so I can turn those lights off. And that, believe it or not, might make a little bit of a difference and improve what we can see here. But I'm hopeful that this next image is going to be pretty good. We're almost there. So one of the things you'll notice while we're sitting here, I'll say this, is that these are all black and white images. So a camera like this one only just records the light that is making it to the chip. It doesn't really care what wavelength the light is. It doesn't look that much better. I'm gonna run downstairs and turn the lights off, but I'll just finish this thought. So when you take a color image in astronomy, what you do is you take an image through a filter. Oh, and look at this. It's actually using a red filter right now. So I'm going to change over to a luminance filter, and that's going to, I think, improve our experience here. And I'm going to just take a single image. So let's go to the luminance filter. So a red filter would be essentially a piece of glass that only lets red light through. So what you do is you take a picture through the red filter and you get information about all the red light that's coming to you from the galaxy. And then you do the same through a green filter, and then you do the same through a blue filter. And then there are programs like Photoshop and other programs that can process images where you can put all of these 3 colors together into a grand color image. And if we have time and interest, I'm happy to show you how that can be done. It's kind of a neat process. You might wonder, how does a color camera work then? Like you've got an iPhone or some kind of a phone probably that takes pictures, or maybe just a camera, and you don't have to take 3 pictures to get a color picture there. And the way that works is the camera chip actually has a series of filters over it. So some of the pixels are detecting red light, and others are detecting green light, and others are detecting blue light. And so your camera on the fly puts these together to produce a color image. So tonight, all of the images that you'll see coming straight out of the telescope will look black and white to begin with. But if you take the time to take images through several different colored filters, then you can actually put together a color image with the images that we get out of this camera. All right, so now we got our 90-second image coming through the luminance filter. The luminance filter doesn't distinguish between colors. It takes all of the photons in. And here now we're seeing something that's looking a bit better. And I'm just gonna quickly calibrate this image. And I'm not gonna explain what that means, but it really, well, maybe I will later if we have time. But you can appreciate that there's a little improvement there, isn't there, when we calibrate the image. I may also be able to adjust the contrast a little bit and get a little bit of improvement here. It's it probably would be even better if we took an even longer exposure. So this is a decision point for all of us. Would it be more interesting to go to a new object and look at some other things? Or would you all be interested in, say, going to something like 180 seconds or 240 seconds and seeing if we can go deeper and get an even better image? I wish I knew how to poll in Zoom. I'd try to poll the audience, but maybe, I don't know, how should we do this? Let's take a vote. You know how to use your thumbs up? Hello, I don't know what that is. Let's
Can I
try,
ask a question while perhaps you take a picture?
let's say it again.
Can I ask a question while you perhaps take a picture?
Absolutely, but first I need to know if we're moving on or if we're gonna go for a longer one. Let's do it this way. If you wanna move on, give me a thumbs up. And the other choice is going to be to say, go for a 240-second exposure. So are we moving on? If so, give me a thumbs up if you know how to do that on Zoom, but you can do it with your hand too. What did I just offer? Moving on. If you want to see a longer exposure, raise your hand or give me a thumbs up. I'm getting many thumbs ups, Okay, so we're gonna go for 240 seconds and I think we're gonna get a pretty awesome picture here. And don't worry, we'll still get to go to some other things, but I think we'll get a really nice exposure. I'm gonna run downstairs and turn the other lights off, and then I'm gonna come up and answer the question. But you could ask the question, the students might be able to answer it. I'll be right back.
Well, I guess while Miss Odin is gone, just a quick point on what exactly calibration does. You may have noticed that when she calibrated the image, some of the texture, some of the like lines across the image went away. And those lines are just texture on the camera chip, just from the way it was made. So the calibration uses just like flats and dark images of just maybe the back of the dome or the sky at dawn when you can't see any stars, and it subtracts all of the noise from the image so that you get a clearer picture of what you're trying to look at.
That is an excellent and succinct explanation, Claire, that is better than I think I would have given. So thank you. All right, was there a question?
Yeah, I wanted to ask you about the resolution of your telescope. Is it possible to see any gravitational lensing phenomena?
Oh, that's a good question. I will, I don't know. I don't know the ballpark size of.
I mean, we see these pictures, of course, all over the internet, but I never thought about exactly whether a telescope of the size that you can practically have in a school actually is capable of seeing that.
It's a great question. So this field of view that we have here is about a 1/2 degree by 1/2 degree, which is kind of similar in size to the full moon. So if we took a picture of the full moon, I can't remember whether the full moon would be a little bit smaller or a little bit bigger than the size of the camera chip. Bigger. Thank you, Lexi. I make the students do the calculation in their astronomy research class, so she knows. So it's a little bit bigger. Okay. So it's actually this is quite a large field. And I think most of those gravitational lens images that you see are
very high resolution,
taken with rather large instruments, which probably means that they're quite a bit more zoomed in than this. So I don't know. Maybe there might be some. There might be something. It's an interesting question. I don't know the answer. Sorry about that. But it's a good one. What else? What other things are people thinking about, or would you like to talk about?
See what the spirals are that we're seeing?
Great question. So the galaxy contains lots of gas and dust, and all of the material is orbiting. It takes a long time to orbit, like, I don't know, tens of millions of years or something like that. But it's all orbiting. And these spiral arms are really regions where the gas gets compressed as it orbits. And when that happens, stars are formed. And so the spiral arms are regions of star formation. And because stars are being formed, those areas get illuminated. Yeah, so, and then of course, the center of every major galaxy contains a supermassive black hole. So there are lots of stars and things located in there, but also a supermassive black hole. Okay, it looks bad, but don't worry. I had just adjusted the contrast for that last image, and so it didn't look as good for this one. So here again, as Claire mentioned, you can see this kind of diagonal pattern here, and that is a pattern that results from the manufacturing process of the camera chip. And with our kind of post-processing, we can kind of just take all of that away. So I think we've improved here. What do you all think? I think it's a bit better and clearer to see. And now you can appreciate why sometimes if you look online and see an image that an astrophotographer has taken, it'll say like that this is an assembly of 9 hours worth of images or something like that. And so what you can do is you can extend your exposure length, but you can also take like 10 240-second images and combine them all together. And that process will also improve the overall look of the images. So you can really start to go down a rabbit hole here, a good one, and have a lot of fun working toward really high quality images. But I think in 240 seconds, we've gotten a lot of nice detail here. And I'm happy for you all to see the difference between 30 seconds and 90 seconds and 240 seconds. Does it look better to you? Was it worth the wait?
Yes.
Yes. Okay, so now I think we should move on to something else. The something that I feel like I should be saving these images. I wonder if I am saving them. I better just do that. Would you like to have that? We'll post them somewhere. So I'll save that. And where am I going to put this? I'm just going to make a new folder if I can. Yes, there. New folder. Alumni class. I'll put it right in there. And what was that? M101. We'll get the alumni the alumni office to post these somewhere. We'll figure it out. Okay. Where are we going next? Oh, that's not what I want. All right, so the other thing I definitely want to show you tonight is the whirlpool. No, not the sunflower galaxy. The whirlpool galaxy. And where is it? Oh, here it is, I think. Yeah, all right, go to. It's right nearby the Pinwheel galaxy. And these two, I think, are some of the most spectacular objects in the sky if you have a telescope that can take pictures. If you don't have a telescope that can take pictures and you just use a telescope and look with your eye at these things, you won't even, you really won't see anything. In fact, if you were all here visiting me in person and we looked through the telescope, we wouldn't see all that much if we pointed the telescope toward these objects and looked at them. This camera that we have is just so awesome that it allows us to see things that the human eye really can't see. So we're going to do the same thing. We're going to do a 30-second image to set things up. And then I think Lexi's going to go again, right? And tell us about the object. And while she's doing that, we'll take a longer exposure so that we can see that. So why can't you have the same enjoyable experience when you look with your eyes? Well, your eyes are kind of taking very short exposures all the time, right? It's basically instantaneous. You don't have any ability to integrate the light over a 30-second period. And also, our eyes just aren't as sensitive as this CCD camera chip. Look at that thing. Isn't that amazing? Okay, I'm going to go for the 240 seconds, and then I'm going to turn it over to Lexi.
Okay, so we're at the Whirlpool Galaxy, also known as M51. It has a magnitude of 8.4, which is slightly dimmer, actually, than the one that we just looked at, which was a 7.8. It's also 31 million light years away, obviously known for its like amazing spiral arms. And if you can see on like the right top corner, there's like another section that's actually another galaxy called NGC 5195. And if this was in color, it would be like kind of yellowish. And those like two galaxies actually like interact with each other. So the NGC would actually like interact with the spiral arms of M51, which is like pretty cool. And of course, as we talked about before, the compressed like hydrogen within the arms is like where all the star formation would happen within like the Whirlpool Galaxy itself.
Excellent, Lexi. Let me try to, while we're waiting, let me try to help you to appreciate how this looks if you look at it through the telescope with your eyes. I think it would be something like that. If you're just doing visual observing, even when you're looking through this wonderful 20-inch telescope, you'll see two dots and you'll be able to see that there's something going on and that they're not quite star-like, but you really can't appreciate what is happening here. You can't appreciate the majesty of this object without having some kind of a camera attached to your telescope to help you to see it. Unless, I guess, maybe if you had some like an 8-meter telescope that you could look through or something, maybe you could get something like this. But you really need to have the ability to photograph some of these things in order to really appreciate them. So again, it's unfortunate that you're not all here with us, but on the other hand, this is an experience that we really typically don't get to have at Alumni Weekend because usually we don't have the camera attached to the telescope. That is something that I think is going to change because I have a new camera on the way. And with that new camera, I'm going to be able to have an attachment to the telescope that will allow me to flip very quickly from visual mode to camera mode. So right now it takes me about 15 minutes to get the camera off and about 15 minutes to get it back on. So there's no way to do everything in one session, but soon I will be able to show you visually something like the Whirlpool Galaxy. And then just with the flip of a switch, I can sort of divert the light to the camera and I'll be able to take a quick image and show people that kind of thing on the fly, which will be very nice. And this is also a good place to mention that the observatory has benefited greatly from the generosity of the Abbott Academy Association over the years. And then some of you may be familiar with the Abbott Academy Association. They are a wonderful group that allows students and faculty to apply for funding for things that they think will make Andover a more wonderful place. And some of those proposals are accepted. And so the telescope that we currently have, this awesome 20-inch plane wave telescope, was funded in part through an Abbott grant, as was our current camera. And this new camera that I have coming was also funded through an Abbott grant. So they've been very generous over the years. And we really appreciate that. And actually, Abbott Academy has a kind of cool history. They had a very special telescope, an Alvin and Clark telescope, that they purchased in, I think, maybe 1890 or something like that. And so the women of Abbott Academy had quite a wonderful instrument back in the day. One of the things that our camera, one of the features that is unfortunate about this particular camera is that there's a line of pixels that acts differently than the rest of the camera chip. And it shows up on longer exposures, but there's a way of fixing it. So I'm gonna do that really quickly. And that is to remove the bad pixels. So what is happening here is we can tell the software where this bad column is. And what it does is it takes the pixel values on either side of the column and it just averages them and replaces those pixels with the average of the pixel values on either side. So I'm just going to do that right now and you can see it go away. It's like magic, isn't it? That's a terrible thing to do if you're doing science with the camera because it's pretend, it's not real. But it's a great thing to do if you're taking astronomy images because it makes them look better. So I don't do that all the time, but I do that here when I'm taking pictures. Now, there's some really cool things happening here. Someone was asking about what was going on in the galaxy. So now we can really see these spiral arms here. You can begin to see some little, these are like probably clusters of stars that are forming in here. These bright areas probably are actually involving many stars. And you can also see here this kind of darker area. That's a dust lane. That's actually dust that's blocking the light that's behind it. And so it looks darker and you can see this other galaxy. It's really, I mean, I think it's a pretty awesome thing to behold myself. Does anyone else have a reaction that they'd like to share?
Beautiful picture.
Do you like the Whirlpool galaxy?
Sure.
Yes? I see some nodding of heads. Maybe you haven't all been on Zoom, or maybe you have. This is actually what my students do on Zoom too. They don't really talk to me very much. So actually, maybe you guys have been in class all year and you're just not letting on.
I find that very interesting. I just wish we could see this in color. I think it would be spectacular.
Oh, all right. So let me see.
Yeah, it's beautiful.
Do you want to see? I'm trying to remember. I might have an image of it in color. Hang on for a second. M51. I'm going to my Dropbox really quickly. I'm not going to spend a lot of time poking around, but I was, I think I have M101 in color, maybe. I thought earlier today that it might be cool to show you all how to make a color image, but if we do that, it'll basically eat up the rest of the time we have together. And I suspect you might like to see some other things. But this is the previous object, M101. And this is a composite color image that comes, these were taken with this telescope. In the last couple of weeks, I've been taking some images thinking about you guys. And I was thinking that if it was cloudy tonight, we could really go in this direction and I could show you how to assemble color images from the red, green, and blue images. But I don't know if that helps. I don't have a picture from our telescope of the Whirlpool galaxy, although I have all the raw materials, we could do that. But like I say, I don't actually think it's the way we should go. But let's just do this. Let's just look it up. We'll see someone else's color image. And yeah, this is probably, yeah, NASA. This is probably an image from the Hubble Space Telescope, I'm guessing. So the Hubble Space Telescope is a bit nicer than ours, and the images are even better. But this is also probably, many hours of imaging combined. So we could do much better with this telescope if we took the time and maybe spent 8 hours of telescope time assembling images and carefully combining them. But yeah, there are some nice images out there on the internet. So that's worth that's worth doing as well. I hope I haven't now made this seem like a disappointing image, but I think it's pretty cool that we can get this on the fly. How long was that? 4 minutes, 240 seconds. Not bad for a high school in Andover, in suburban Boston. So let's keep going because
Will
there.
you save this one for us as well?
Oh, yes. Thank you for saying that. I would absolutely have forgotten. So please keep me in line. I'm easily distracted. So what is this one? Was it M51? I think so.
Yeah, it is.
M51. All right.
Can I
Hello,
ask if,
Caroline. Good evening. I'm with my son, and it's very fascinating. He had a question. He was wondering if we could look more closely up to a planet and to see what happens around it. Do we have that capacity?
Oh, that's a great question. I don't think there are a lot of planets that are well positioned right now. And in fact, most of the really wonderful images of planets that you see online are taken by space probes that go to those planets and either fly by or orbit them. So with a ground-based telescope, you can see a little dot, and that's a fun thing to do. It's a very nice visual experience to look at a planet, but but if you want to really get up close and personal with the planet, you have to send a probe there to see it well. I think the Hubble Space Telescope might also be able to get some higher resolution. But like the pictures that you see of Pluto that were taken by the New Horizons spacecraft a couple of years ago are the best images we've ever had of Pluto. And prior to that, we didn't know a lot about the surface features of that planet. So that's the way that's done. I do see Mars on the horizon, but I think it's going to be too close to the horizon for us to get a good view. And you'll notice there's nothing else really, there's nothing else that's really a good option for us. So I'm sorry about that, but I think planets might be out for this evening. However, if you're local, you can come see me sometime and look through the telescope, and we can check out some planets, maybe next winter.
Next reunion.
Next reunion? Oh yes, because you're far away. Yes, and he'll be at a good age for that as well. All right, so now I'm gonna go to the Ring Nebula, and I've got to move the dome. I'll be right back.
I have a question that maybe a student can answer. When you're doing color superimpositions, how do you account for the change in time between the different exposures so that they line up?
That's a great question. So the telescope is tracking with the rotation of the Earth. And so the object stays pretty well in the same place from exposure to exposure. And it isn't changing rapidly. Like when you're taking a picture of someone playing soccer, you got to get all three colors, you've got to get all three colors at the same time, which is why those digital cameras have filters for individual pixels. But here, the object, most of these things are not changing very rapidly. And so it's no problem. You can even take your red images on one night and your green images on the next and the blue images on the next if you want to. But the telescope is tracking with the sky. And so I'm not sure which of those questions you were asking. And so in what is my typical fashion, I said two things, hoping that one of them would be what you wanted to hear. But
Yes, thank you. Yes, you got it.
You know me now because you were here for my morning class, and that's how I do it, because I don't always know exactly. All right, so here we go. We're at the Ring Nebula. This thing is bright, and actually, if you were here, this is one that we could see really easily through the telescope. Like you can actually see this one. So this is just going to be a 5-second exposure. I think that'll be sufficient. Maybe we'll want to go to 10 or 20 seconds, but after that, it will actually be overexposed. One moment, please. It looks bad because of the screen stretch I have on here. So I'm going to change the medium. And there you go. Who's talking about this one?
That's me.
All right, go to it.
All right, so the Ring Nebula was discovered a very long time ago in 1779. It's about 2,000 light years away, and it's estimated to be about 7,000 years old. So it's pretty old, like in our terms, but not super old in terms of, you know, other celestial objects, which is pretty wild to think about. It's a planetary nebula, which has nothing to do with planets. So it's an interesting choice of names, I gotta say. I can't explain that one. But it is the remnant of an old star that didn't go supernova, but it's a star kind of like the sun, or it was before it became this nebula. When stars like the sun get old, they expand a lot from their kind of like regular mid-sized orange ball type thing to big red giants. And when they do that, they shed some layers of gas from their outer shells, and that's what creates that kind of bubble look that you get with the Ring Nebula. So you can, I guess you can kind of see it, even though it's a little bit blurrier than some of the Hubble images you might have seen of it. You can kind of imagine how, you know, it's the layers of a star that has slowly drifted apart over thousands of years. You can kind of see the circular nature of it, and then that little bright point in the middle that you can kind of imagine is something there. Usually there are white dwarfs in the middle of planetary nebulae, which are pretty hard to see for a lot of amateurs. But M57 in particular is one of my favorite objects in the night sky, and it's one that I actually hope to image myself this summer. So we'll see.
I'm glad I assigned this one to you then, Claire. So the white dwarf, can you see it right there at the center? It's dim, but it's there. And just for kicks, let's go for a 15-second exposure. And some of this will probably become overexposed, but we may then be able to see that white dwarf a little bit more at the center of the Ring Nebula. So the Ring Nebula is one that if you point even a smallish telescope, like an 8-inch telescope, and you get it on the Ring Nebula, you will be able to see it. It's dim, and it's a little bit of a challenging object if you haven't done a lot of telescope observing, but it's a really good one. It's a nice challenge for visual observing. And I think here you can see it a little bit more now, right? That white dwarf right at the center of the Ring Nebula. So this one is one where if we had a lot of time, it would be fun to take a color image. Now do you want to see the Ring Nebula in color? Might as well look at a color image of this one, because it's actually pretty cool. See that? It's got like a rainbow look to it. Now, you won't be able to see this kind of color through when you're visually observing the telescope. It looks black and white. And that's because you have sensors in your eyes that the color sensors in your eyes really only trigger when light is relatively bright. And when you may have noticed that when you're outside in the dark, everything basically looks black and white. And in the same way, when you're looking through the telescope at a relatively subtle object, it will look black and white to your eyes. And so you have to have you have to take images to get this, to be able to see the color. But it is quite beautiful, isn't it? It's really a good one. All right. It's already 10 o'clock, but there's one more
Save
thing
it.
I'd like. Oh, sorry, go ahead.
Save
Did you
it.
have something?
Request to save it.
Request what?
Just save it. Save the picture.
Oh, thank you. You really have to keep an eye on me. And I didn't save the original images, but I'm going to put some in. The Ring Nebula, what is the number? M57? Claire, do I have it? I think so.
Yeah, you're good.
What else did we saw M13 and one or two others. I'll get the students to help me. I think I've got some images that I've taken at other times of those objects that I'll put in. And if I don't, I'll go back on the next clear night and get them for you, because I want you to have a record of this evening. All right, I want to try for one more object. You're welcome to go if you've had it. I know I've gone over time here. What's that?
Can we see Sagittarius from the Northern Hemisphere?
Sagittarius. This is really what I want to show you is the Dumbbell Nebula, M27.
I want to know if you can see Sagittarius
Yes,
in
you
the sky.
can. It's very close to the horizon, though. You're thinking about looking at this toward the center of the galaxy. It's
Yes.
close to the horizon, I think. That's a good idea. Help me find. I think we want M27 if we can get it, though. Let me just see if I can remember. I have this other program that's a bit better for helping me to find these things. Oh, M27, where is it? Let's see here. That seems to be very close to the horizon. That's not a good choice. Well, maybe that's it. Unless you want to end with a globular cluster. And I feel like I've promised you one more object. And so now I've got to come up with something here. M102 might be interesting as well. Let me just take a peek. Now I'm just ad-libbing. Never a good thing. Oh, and this is the other thing that really is a bummer. You should always, if you're looking up M anything, make sure you put astronomy, because invariably you'll get weapons and things that you don't want to see. Oh, no, that's M101. I want to see a picture of M102. M102 images.
Caroline, while you're looking, Claire mentioned work this summer. Is that done at the at school, or where does she do that work?
Have my own telescope, which is pretty fun. I
wow.
just upgraded it. I have an 8-inch. So yeah, I'm hoping to get some cool astrophotography done at that this summer. I'm an amateur. I don't have a ton of experience, but I'm gonna build up some of that experience this summer.
Great.
There goes the dome. All right, so this is going to be a good one, I think. We'll do one last one. Troy, you might also jump in here. Where is he? If he's still here. I actually don't see Troy. We may have lost him. But we do pretty much wrap things up over the summer, but a couple of students are going to be, I'm going to go straight for a 240-second exposure of this one. A couple of students are actually going to be working on a project this summer, because now that we've experienced Zoom, we realize we can sort of keep going with things sometimes. So they're going to be modeling a variable star. Excuse me. We've already taken the images, and we just need to do the analysis.
Can I ask another question?
Yes. For some reason, I'm coughing. So students may have to answer.
When you have good low humidity vision, like in a desert, and you can see the Milky Way clearly, which direction are you actually looking? Are you looking towards the center of the galaxy, or are you looking out? Where?
Oh, I see what you're saying. So we're in the
we're in an arm.
Embedded in the frisbee of the galaxy. So it's like a great disk of gas and dust. And if you're looking toward the constellation Sagittarius, then you're looking toward the center. And you can see this great kind of band of stars in the sky. And that's just it's like what we perceive of the Milky Way from our place within it, the Milky Way galaxy. And so if you start at Sagittarius and then go along the Milky Way in either direction, you would be going away from the center. And so it depends on what direction you're looking in. But if you want to look toward the center, you want to look towards Sagittarius, and there's a lot of gas and dust in between us and the center of the galaxy. So it doesn't look particularly bright when you look at the Sagittarius constellation. But that's where the center is. And if you if you look with infrared in that direction, it looks very bright because infrared radiation can pass through gas and dust much more easily. And there's a lot of energy being produced around that central black hole. And so it is possible to detect it. You just have to be in the right wavelength, the right part of the electromagnetic spectrum in order to really detect that. There's a great NOVA documentary called Monster of the Milky Way that is a really wonderful, they talk a little bit about what I was just talking about, but then they also talk about this kind of realization that astronomers have come to surprisingly recently about these black holes, these supermassive black holes being contained at the center of basically every major galaxy. So that's a really nice NOVA documentary. I think another one just came out recently where they talk about the team that imaged that black hole. And I have not yet seen it, but my good friend, Dr. Jerry Hagler, who teaches biology here and is interested in astronomy, told me that that's a really good documentary, but I don't remember the name of it. And the other one that's really good is called Runaway Universe. And that's where they talk about the research that was done they were trying to figure out the rate at which the universe was slowing down, but then they realized that actually the universe is accelerating, which means it's expanding, and it's actually the rate of expansion is increasing. So that's another really good one, Runaway Universe, if you're looking for movies to watch. All right, so here we are. We're going to do a couple things to try to improve this. Number one, we'll calibrate. And then I'm going to try to do a little bit of a stretch here, medium. And this one is seems to be a slightly more challenging object. You can certainly see that there's a galaxy here, but I think this is one that would probably benefit from a longer exposure. There's probably some interesting stuff out here that we're not quite getting, just because I haven't. I don't think I have a long enough exposure yet. Anyway, that's the way these things go sometimes. So I've completely lost. Oh, let me stop sharing. I don't want to keep you guys for too long. It's 10:10. I think we've gone a bit beyond the plan. But I really appreciate you all showing up and hanging out and looking at some astronomy objects today. And I'm not in any hurry, so if you want to hang around and ask questions, feel free. But I also want to let you know that I value your time and I don't want to keep you longer if you're ready to go. So thanks a lot. And thank you very much to the students for preparing your comments on the objects. I think that really added a lot to the evening and was really good. So thanks again for that.
I would like to ask if the Abbott Academy Observatory is still functioning in any way.
Oh,
having the dome there.
That's a great question. The Abbott Academy had this wonderful telescope, as I mentioned, and at some point, I'm not exactly sure when, the telescope was sold to a private collector who had a wonderful collection that is now actually at the State Museum in South Carolina. If anyone's ever in South Carolina, they have a really wonderful collection there. But that fellow knew a friend of mine named John Briggs, who had gone to Andover, and he had a wonderful experience using the Abbott Academy telescope and wanted it. And he had a bunch of antique telescopes of his own. And so he traded with this guy and got the Abbott Academy telescope. And he now lives in Magdalena, New Mexico, which is a tiny little town south of Albuquerque with very dark skies. And he has that Abbott telescope. And I've had a chance to look through that. It's a wonderful telescope. And by the way, it's really good for looking at planets. You get really good views of planets through that telescope. The dome itself down at Abbott campus is part of the artist's apartment, which is like an architectural piece of artwork that is owned by the Addison Gallery. I don't completely understand how it works, but I guess they had an architect that designed this apartment that they refer to as the artist's apartment. And the dome, I think, is maybe part of the bedroom or something. The dome was a kind of special historical dome because it turned on cannonballs, on cannonballs. And the mechanism, I'm sure, was not great, but that's an unusual thing. And there are only a few of those observatories left. A couple of years ago, they renovated the dome. I guess there were some bugs that were getting into the artist's apartment, and they actually took the cannonballs out, so it no longer rotates. They still have the cannonballs, I hear, but it's not really functioning as an observatory anymore. So kind of a bummer, but it's really nice to know. It's nice for me to know that my friend, who I trust, has that Abbott telescope, because I know he's taking good care of it, and it's good to have those things at least in good hands. It's nice to know that an alum of the school has the telescope.
My sister was in the class of 1947 at Abbott, and she got hooked on astronomy there because of their having that observatory. She majored in astronomy and mathematics at Mount Holyoke, and then she worked in astronomy for about 15 years after that before she got married.
Wow, that's pretty neat. It's really neat to hear that, and I'd like to make another recommendation to you all, and that is there's a very good book that I read with my astronomy research class this term called The Glass Universe, and it is about a group of women that worked at the Harvard College Observatory in the early part of the 20th century. And they made all kinds of discoveries that are kind of fundamental discoveries that students learn about nowadays. And a lot of these were made by these women that were working at the Harvard College Observatory. So it's a really neat historical book, very inspirational to realize who is making all of these discoveries. And I highly recommend it. It's a really good read. And it sounds like it might be something that you would connect to, given your sister's interest and career in astronomy. So
Her first job after college was at the Harvard Observatory.
there you go. It's really, it's fascinating. Yeah, there are many examples actually of women working in astronomy, I think long before other fields were really welcoming women. Astronomy seems to have been open to that. And of course, I'm sure it was it's interesting and wonderful to learn about these things. So if any of you are interested, The Glass Universe is just a great book. And it's also kind of fun to, I had this kind of fun experience this spring. I realized that the author, Davis Sobel, there was a place online where you could write a little note to her. I looked her up, and it said, you know, if you want to contact the author, put it into this box. So I did, and I said, would you ever want to come and Zoom with my class and, you know, talk about this book? We're reading it. And I thought, I think that it was clear that she had an agent when I typed into this box, and usually that means you're going to have to pay. So I thought, well, this is never going to work out, but you know, it's not going to hurt to send her a little note. And sure enough, a couple days later, she wrote back to me by email and said, sure, I'd love to come to your class. And by the way, her agent was an alum of Phillips Academy and had happy experiences at Phillips Academy. Probably told her that she should, you know, go ahead and do this. And so we had a great time. She came to the class by Zoom, and the students had a chance to share some of their thoughts about the book, and she shared some of her thoughts about the book, and it was really a lot of fun. I see here someone asking for other book recommendations. How I Killed Pluto and Why It Had It Coming is a pretty fun read. Lexi and Claire read that one in the winter term astronomy research class. And the other one I really like is The Hunt for Vulcan. And all of these books give sort of different, they provide some perspective on the history of astronomy. So they all take place during different time periods. But they, I think, do a really nice job of kind of giving a sense of, I don't know, the adventure of doing science, and maybe how that adventure has changed over time. But if you read those three books, you're going to get some really good perspective about, you know, how science has been done over the years. Weihan, you should get it. You'll like it. It's a good book. I'm reading the, I'm just now catching up on the comments in the chat here.
One question while you're looking, does it get cold in there in the winter?
Yeah, I didn't have a chance to give you a tour, but I'm upstairs in the observatory mostly to set the you know, to kind of give you the ambiance of the observatory. But actually, we have a control room downstairs, and that's normally where you would sit. That's where the main computer is. And so when the students are running the observatory in the wintertime, they come into the observatory, into the control room, they do their thing. And, you know, if an image comes out badly, they might run up the stairs to make sure the telescope isn't pointed at the dome or something like that. But most of the work is done from there. And in fact, sometimes if the students aren't available and I'm feeling lazy, I just log in from home. I can sit on my living room couch, log into the observatory computer, set up the imaging for the night. And we have a cloud sensor, a weather sensor on the roof of the building. So it's totally safe. So if you know, if the weather gets bad, it shuts down automatically. And we can take, I could set up all of the imaging that I showed you tonight. I could just set it all up ahead of time and push a button, and it would just run through everything for me. So that's kind of necessary because I can't stay up all night because I need to teach my classes during the day. So when you have this automated system, you really end up getting a lot of images because we basically image through every clear night. We start when it gets dark and we go until dawn. And most of it is not these fun images that you saw tonight, but the kids are actually, they have science projects. And so we need to get data. And so we do that all through the night. And you have to have an automated system like this if you're gonna do that. But it is a pretty cool system. It's amazing. And you know, yeah, it's awesome. It really is.
I'm stunned by the clarity of some of these shots, Caroline, and the light pollution you alluded to earlier. Is that a lot of it filtered out by the computer?
I think that the objects that we're looking at are bright enough that compared to the sky background, to the light pollution, everything is just okay. But when you start, when the light pollution starts to become a problem is when you start trying to look at things that are dimmer, and you just end up, you need to have a difference. You know, the thing you're looking at needs to be brighter than the sky. And so, you know, when you're doing science, you're always trying to push your equipment to kind of do the best science it's capable of doing. And so the sky background just limits what we can do. So for example, let's say that we're trying to measure the rotation period of an asteroid. In Andover, that for the, maybe some of you are familiar with magnitudes, maybe we need to probably measure something that's brighter than 17th magnitude. If we went and put this telescope in New Mexico in a dark spot, we could go much deeper and measure much dimmer asteroids. And so we can still do a lot from Andover. And I think the students get so much out of being able to be in the dome with the telescope and kind of, they can kind of see what's happening. And so it's totally worth it to have a really nice telescope in Andover and just do the best we can. But absolutely, it does, the light pollution does eventually limit what you can do. But it's okay. We have access in a pinch to a telescope in New Mexico that's the exact same telescope as this one, a plane wave 20-inch telescope under much darker skies. I can't use it all the time. It's controlled by Middlebury College, but through a series of connections, I've managed to kind of worm my way in there. And if I need something, I can just ask this very kind fellow at Middlebury College to take some pictures for me, and he sends them to me. So there are ways to make things. Got to be nice to people. Jay, yes, it's a special Odin wormhole. That's right.
Well, Caroline, Claire, and I think, oh, Lexi, I see you right there as well. I am so grateful for your time today, and I'm so excited for the photos that you took and to share them as well. So I'll be sure to get those out to this group. I know that others might have to jump off. I'm happy to leave the call open. I do have to jump off myself, but folks can stay on for however long they'd like, unless Caroline, I know that you also might need to scoot as well.
Am I a co-host? Yes, I am. So I'm fine. I'm happy to stay on if people have questions or if they want to talk some more. And thank you to you, Olivia, for your help. And yeah, it's great to talk to you all. And thanks for taking the time to join us tonight.
This
Thanks
is
very
always
much. Thank you very much.
Thank you very much.
Sure.
Thank you.
Okay, bye.
Okay, see you. Nice to see you, Mr. Broderick and Wayne.
Good. Good to see you, Caroline. Always
Nice to see
fun.
you again. Good to be
Yeah.
back in class with you virtually.
Absolutely.
all right. Caroline, this is always one of the events at Reunion that I wish I could attend, but I'm always at somewhere else on the golf cart, getting someone.
So you finally had your chance.
Exactly.
That's
And
great.
now I will make you officially the host.
Okay.
And
I'm glad to hear the Abbott Academy Association supported you. I was treasurer of the Abbott Academy Association for 8 years, many years ago. And I think it's just the kind of thing that we really like to do.
I would say that they've been more than generous. They've been really great. I think that they like, one of the things they like to see is they like to see their money put to good use. And we do a lot of good science with this telescope. We talked more about this morning, but these kids really do some good projects, and some of the work is publishable. And so I think they feel really good about, you know, the investment that they're making in the observatory. And it's also a nice thing, given kind of the history of astronomy at Abbott, it's nice to keep it going. And we acknowledge the Abbott Academy Association in all of our publications and everything. And so it's nice in that way to perpetuate the nice tradition of Abbott.
Well, I'm glad they supported you, and thank you again for this evening.
Sure, no problem. It was great having Sister too. Thanks, Claire. You've been great today, and thanks, Lexi.
I'm
All right.
happy to stick around if anyone has any questions or anything.
What is the main source of light pollution in the Merrimack Valley? Is it?
I think we're getting some light pollution from Boston and some from Lawrence. And believe it or not, I think we're getting quite a bit, we're producing quite a bit of our own light pollution. We've got a lot of street lamps all over campus, and it's understandable that you'd want those for safety, but in recent years, everybody's been going to these LED lights, and they're a bluer light. There's a lot of blue in there, and that the shorter wavelengths scatter more when they go up to the sky, and so they produce more light pollution. So that has been a problem, and the reason I think it's coming from the campus is that when it snows, those streetlights, the snow reflects the light, and the images get much worse when it snows and when there's a layer of snow on the ground. So that makes me think that our own lighting on campus is probably producing a lot of it.
Sometimes when the moon is out too, it does a lot of damage in terms of light pollution. There are some nights, I think there was one night in the winter where, we had the combination of fresh snow and a full moon, and it was very bright outside. Even I could notice that when I was doing my homework in my room late at night. So yeah, that was not a good night for imaging, even though it was pretty clear, I remember.
It's actually pretty fascinating to me that when you have a really fresh layer of snow and like the moon, like Claire says, the images are basically ruined. You just have a lot of sky background. But the snow can remain, and after a few days, even if it's been very cold, stuff happens and it settles, and it's not nearly as reflective after a few days. So, and then of course it's much better when the snow goes away altogether. But even just a few days will kind of dull the snow so that it's not causing quite so much trouble. John, you've been quiet. Anything you want to ask or add?
Are you talking to me?
Yeah.
Oh, okay. I was curious, were you able to see that that asteroid thing that came through the solar system? I think it was a year or two ago. It had a funny name, Oh My something or other.
Oumuamua.
Right.
We did not. I'm trying to remember. I think at the time, looked into that. So when these near Earth objects come by, sometimes they're only visible from parts of the Earth. And so I think Oumuamua may have only been visible from the southern hemisphere when it was great enough for us to see it. But that was an interesting object, and it's been in the news a lot because this guy Avi Lev from Harvard has talked about. I mean, it is an interstellar traveler in the sense that it came from outside our solar system, flew by, left. It's not.
Yeah.
It's not bound to our solar system.
Right.
Has been stirring the pot and trying to make an argument that it could have been sent by aliens.
Right.
And other scientists have been rather irritated by this. It seems to be, I like when people bring up ideas and sort of, I don't think there's anything wrong with stirring the pot, but on the other hand, it seems to be a little bit of a self-promotion. I cannot say that.
Okay. Are you, when you operate the telescope, are you always operating at the maximum magnification and range and so forth that you can in general?
Yeah, so the magnification is set for once you put the camera on, the magnification is set by the focal length of the telescope, and you basically the size of the pixels in the camera. So what we can control is the exposure length, and we can take some really long exposures. But, a typical exposure length will be like 5 minutes for us. You get a really nice exposure in 5 minutes, and things don't go wrong. If you go longer, let's say you go for a 30-minute exposure, if a wispy cloud happens to pass by, your whole image can be ruined. So a lot of times it's better to actually take 6 5 exposures and come back if you're looking for a long phone. But I would say the way in which we're maximizing is we're usually trying to do projects that are kind of at the edge of our sensitivity. So like with our asteroids, we'll choose something that is kind of on the dim side, but still something that we can image successfully and get in good data. So that's kind of what we're trying to do. We do an exoplanet project also where we're looking for exotransit. So these are planets that are passing in between distant stars in the Earth, so the light from the star dims slightly. And we try to get exotransits that are kind of the most subtle ones you can get. And yet still get good data. So we're always kind of trying to push the envelope, but still make sure that we're not. So that data is still good.
Is the observatory in its own building on campus, or is it, or where exactly is it on campus, or what building is it in, or near?
Let me pull up an image and I'll show you.
Basically from lands all the way up through Sear. This 4 square mile site will be redeveloped.
Okay.
I don't know what year you graduated, but Evans was the old science building. And this is the Gov Science Center built in 2004. And this is the observatory.
Oh, yeah, very nice.
And yeah, it's good. It's really nice.
Okay. All right, thank you.
Sure.
Yeah, thank you, Caroline and Claire and Lexi. Very, very nice presentation.
All right. Well, looks like we're winding down. So Kelly, thank you for coming to both sessions today. You've been very loyal to astronomy today.
It's very, very nice to see that the school has some good equipment.
Yeah, it's we're very lucky. So thank you so much for coming. And Tony, thank you for your note here in the chat. And yeah, thanks for coming tonight, you guys. Claire and Lexi, you guys are awesome. Thanks for hanging in there. You've been wonderful. They were at both sessions today. They're superstars. So, all right, you guys, have a great night. See you soon.